All right. For those who haven't met me before, my name's Anthony Smith. I'm the Chair of Airworthiness for Gliding Australia. This webinar is the second webinar out of a two-part series in response to a Flutter incident that happened in a LSA motor glider on the 29th of December last year. The previous webinar covered aspects of the flight envelope. This one's going to be talking about the fun and games of Flutter. And right. The quick caveats, as per last time, it's not the purpose of the aircraft incident investigation to apportion blame or liability. The sole objective is part of this no blame culture that we have is simply to investigate and report so that we can prevent further accidents of this nature from happening. I will not reveal the identity of those involved. Now, the details of the event or the incident report has been published in the latest magazine, so the aircraft type's now been shown, which is the Phoenix. I didn't reveal it last time because there's not very many of them in Australia, and you can pretty quickly work out who the owner is from that. If you do know the identity of those involved, please do not reveal their names either verbally or in chat during the webinar. It's really, really important that we have a SAW reporting system or a defect reporting system that members can be treated, can expect to be treated with confidentiality and this no blame culture. If we start blaming people, the number of blaming or shaming, we will start getting the SAW reports and defect reports drying up very quickly. We won't learn anything from out of those incidents that go unreported. I will give a brief rundown again of what happened. There may be a number of attendees here tonight who weren't at the previous one, including the sequence of events. And then I'll start talking about what is Flutter, and we'll have questions at the end. If you do have questions, you can use the question and answer panel on the tool from the toolbar, or you can pop something down in chat, and I'll try and answer things as I go along. So very briefly, what happened? An LSA touring motor glider took off later in the afternoon on a thermal day. Approximately 4 minutes into the flight, whilst climbing, very fast climb at 100 knots, climbing through 3,500 feet, the autopilot was engaged. Now, this aircraft is a bit unique in gliding circles. It's got a two-axis autopilot. It will hold attitude and will hold direction. This was the first time the pilot had used the autopilot. The aircraft unexpectedly pitched over into the altitude hold, and because it was on a very high power setting, accelerated up to and briefly exceeded VNE. VNE on this aircraft is 120 knots true airspeed, at which time the pilot took over the control of the aeroplane and performed a pull-up and wound back the throttle. During this event, a series of bangs were heard with a final louder bang, and we'll talk a little bit about later on. The pilot did carry out a controllability check and decided to continue on the flight for nearly 2 hours. Once they landed at their destination, the pilot noticed that the fuselage tail boom near the vertical stabiliser junction had a severe structural damage. There's some photos from the accident report. The right-hand side of the aircraft is on the left-hand photo, so you've got a 45-degree diagonal tension crack, and there's compression damage on the port side on the right-hand photo. There's a little bit of damage that's hidden under the tail dolly on the left-hand photo at the moment, and the seam down the centre line just under the leading edge of the root of the fin there has been split open as well. So the sequencing, we have a lot of good data points from the autopilot, which also acts as a flight data recorder. Again, very unique in terms of sailplanes in Australia, that we have quite a large amount of these information, including control inputs. At 6:45:08, the aircraft reached its peak speed of 121 knots. 2 seconds later, the pilot had reacted and pulled back on the control column, wound back the throttle, and reduced the speed. At this time, the aircraft roared left. The autopilot applied right aileron, which was partially overridden by the pilot, and there were a number of bangs heard. Now, that in the accident report, the precise timing is unknown. But I think we can nail that down to being at 16:45:10, or just a fraction after, and I'll show you where that occurred later. After carrying out the controllability check, the autopilot was re-engaged and the flight continued. However, the pilot noticed that they had to continuously apply right-hand rudder to maintain straight flight from this time onwards. Now, the pilot had only flown the aircraft for a few times previously, so they weren't particularly experienced with using the autopilot and these long-distance flights. Aircraft landed safely at 6:36 p.m. So the results out of the investigation, the right-hand side of the tail boom failed in tension with that large 45-degree crack. The left-hand side of the tail boom had a partial fail in compression, and there was cracking to around 70% of the circumference of the tail boom. The structure retained pretty good vertical stiffness, so elevator function wasn't adversely affected. But the lateral stiffness was very poor. The aircraft was quite flexible in the left-right direct wobbling of the fin. There was video recorded in the cockpit during the flight with a 360-degree action cam, and there's periods of that flight where you can see the vertical fin physically wobbling left and right. Now, there's been a number of flutter events that occurred on the similar models to this aircraft, which the aircraft is derived from. There's certainly at least one potential flutter event that occurred on this particular aeroplane, where unknown vibration occurred at high speed, and there are two other events which were attributed to the caps of the air brakes vibrating, but there might be something else going on in the background there as well. Again, unknown vibration at high speeds. The speeds that all this occurred at are very similar to the speeds at which the flutter event took place. So whilst the aircraft was being operated beyond the recommended airspeeds, and that's a bit of a grey zone because the aircraft was imported from the US, and the US regulations have a maximum V&E on LSA aircraft of 120 knots. In Europe, the same aircraft has a V&E of 140 knots. So yes, the aircraft did exceed V&E, but not by very much. It was still within the flight envelope, and you should not be experiencing flutter within the flight envelope. The control free play was negligible. The control surface weight and balance was all within the published limits. So we've got a bit of a no fault found at the moment. We suspect there's something funky going on with the type, with other events of this nature having occurred on a couple of other aeroplanes, and I'll talk about those a little later. So the recommendations out of the report are we should seriously look at the airworthiness of this aircraft type and the flutter events with the other aircraft. We don't have any details of those. They occurred outside the country. Pilots should be advised when an in-flight event occurs and resulting in observable changes to the aircraft handling characteristics, the flight should be aborted immediately. I'll also add, if you hear a series of bangs in the airplane while you're flying, yeah, you should be seriously thinking about landing after that. One of the features in the autopilot system did allow a maximum airspeed to be set, and that was not set in this particular example. So in that case, the aircraft, as it approached V&E, would have done an automatic pull-up to try and prevent going through V&E. The last recommendation out of the report was for the GFA to raise pilot awareness of Flutter and to enhance their understanding of what this is and what can lead to this phenomenon. This is what this webinar is partly about. So what the hell is Flutter? Well, it's also known as the field of aeroelasticity. You can go to a technical library and you can get whole textbooks written on the subject of aeroelasticity. It's a very complex subject, and for the purposes of tonight, I'm going to be simplifying it greatly and making some generalizations. If you want to go deeper into Flutter, there's quite a few good books written about the topic, and you can do your own research in that area. But broadly speaking, Flutter is an uncontrolled oscillation or a vibration of the aircraft structure or a control surface in flight. It can affect anything with a hinge on it, so ailerons, elevator, trim tabs, rudders, flaps. It can affect wings, vertical tail, horizontal stabilizer, and even the tail boom under particular circumstances. Every structure and each control system will have a frequency that it will want to vibrate at naturally. This is called resonance. And when you get that, you have very low damping effects. The structure wants to vibrate at that frequency. And mathematically, that frequency is affected by the distance of the center of gravity of that item from the point it's either rotating around or flexing around. So as you move that center of gravity further away from that hinge point or that point that it's bending around, then you're going to be lowering the frequency that it wants to vibrate at. There is a correlation between the frequency that it wants to vibrate at and the speed it will vibrate at. So a lower frequency of vibration for that structure will correspond to a lower airspeed. Flutter is energized by the airflow. Now, aerodynamic forces are proportional to the square of your airspeed. So at some point, there's enough energy available from the airflow to really drive this resonance. And the big caveat here is if the structural system is bumped or disturbed, you need to have turbulence or be doing maneuvers or just bump the controls. Many aircraft, particularly high-speed jet aircraft used by the military, may have flutter speeds that occur inside their flight envelope. They can accelerate through those speeds quite safely and decelerate through those speeds quite safely. But they don't want to loiter or hang around at those airspeeds because of the high risk that the longer they stay there, the more risk of flutter they get. All the flutter testing is done by flying at a set airspead, trim to that airspeed, taking your hands and feet off the controls, and then giving the controls a tap with your hand, or you kick it with your foot, and see what happens. If you have dead smooth air, you're not likely to get a disturbance and you can fly quite fast without getting flutter. Most of the time though, we're flying in thermally conditions where there is a bit enough turbulence in the air that it will kick the controls, just that little bit to get it moving. This very low damping at resonance means that the oscillations can build up to extreme levels, often within seconds. Certainly there's plenty of video footage of things going haywire very quickly, and you've got maybe 3-4 seconds to do something about it before the structure falls apart around you. An example of this came out of the Phoenix with the autopilot recording. This is a recording of the lateral acceleration as felt at the center of gravity. So it's not the accelerations being felt at the tail boom, it's at the center of gravity. It's not a particularly high resolution recording. It's probably only recording a data point every half a second. To get a really good recording, we want to be recording maybe 10 Hertz 10 times a second. If what I think happened, we're probably seeing a resonance of around 3 to 4 hertz, and so you want at least 8 data points per second to capture that nicely. But we can see some background vibration or oscillation happening at around that 1645 mark. The time major ticks are at 10-second intervals. So at about 1645 and 7 seconds, this background oscillation ramps up dramatically. And just after 1645 and 10 seconds, there's a really big kick. And I think this is where the tail boom started to fail with the break in the structure. But you can see just from this very rapid buildup of vibration from the flutter. Flutter and aeroelasticity covers a whole range of phenomena. We're going to simplify it down to the most common forms we're most likely to find within sailplanes. The first one is control flutter. This is the one you're most likely to encounter. It can affect anything with a hinge. So ailerons, elevator, rudder, flaps, trim tabs. It can be caused by the control surface having the centre of gravity too far aft. So as you move the centre of gravity further away from that hinge point, you're lowering the frequency. The speed at which flutter will onset will occur sooner. You can have hinge free play. This allows the hinge point to bump up and down and gives an extra degree of freedom in the movement of the surface. There is footage of an F-117 stealth fighter on the internet at an air show in the US, where it's doing a high-speed pass along the runway, where there's a brief buzzing sound, and then I believe the left outer wing snaps off. The aircraft does a series of snap rolls before the pilot finally ejects blue side up and safely lands. The aircraft then goes and crashes into some houses further away from the airport. That was caused by the wear and tear of worn bolts in the aileron hinges. So it wasn't actually hinge free play, but in terms of the pivot, but the hinge itself, the mounting bolts, was being allowed to slop around and move around. And again, that buzzing noise was the aileron fluttering, and it lasted just under 3 seconds before the wing failed. Control system free play. I've experienced something like that in a military aircraft that I used to support. VNE on this particular aircraft was 405 knots. There was rudder flutter at 300 knots. We checked everything we could think of at the time to try and work out why this was fluttering at 300 knots. We checked all the control systems and the linkages. Turned out it was again the big mounting frame that the rudder bell crank was mounted onto had free play in the bolts, and so this whole frame was slopping around slightly due to input from the rudder, and it's causing a feedback loop causing rudder flutter. So when you start thinking about control systems, you've got to think of not only just free play in the bolts that connect push rods together or sloppy low tension cables to the rudder. You really got to look at the bearings to the bell cranks and what those bell cranks are being mounted to and how they're attached to the structure as well. And lastly, the one that I think has actually had a bit of a input into the events with the Phoenix, undetected damage. Anything that reduces the stiffness of the structure will decrease will change the resonant frequency and increase the risk of flutter. So in its simplest form, the control surface is simply and violently swinging back and forth, often hitting the limit stops. And for many of the small chord control surfaces like elevators, that frequency is in the order of 20 hertz. That's within people's hearing range. You can hear it buzz. Generally, the oscillation is too fast for the structure or the aircraft to respond. when you get these high speed, high frequency vibrations, the structure doesn't have a chance to bend backwards, forwards, or twist around. It's simply not, the inertia of that structure is too great for it to move very far. But what you will do is feel it shaking the crap out of the control system. You'll feel it through the rudder pedals, you'll feel it through the control column. Damage to the control surface hinges, control stops. That's what results. You'll either have the control surface self-destructing, you'll have the hinges falling apart, or the control stops fail, and then the control surface then starts hitting what it's attached to, the wing, the horizontal tail, the fin. So you can get a more complicated version of this, and this is typically where the control surface is swinging at a lower frequency, and now your aircraft structure has time to respond, and it starts forcing the aircraft structure around. So for the sake of argument, we're going to call this a vertical fin and a rudder. And this diagram works from left to right on the top row, and then from left to right along the bottom row. It starts off with the rudder in the neutral position. As the rudder flaps, for the sake of argument, to the left with a large deflection, it's going to force the fin over to the right. As the fin bends over, it's going to start twisting nose to the back to the left again. That's going to increase the angle of attack and start trying to force the fin back to neutral. However, by this stage, the rudder is now swinging back towards the right-hand side, and you get the situation not only where you have the fin bent over to the right with an increased angle of attack trying to return it, you've got the elastic forces of the structure trying to return it, and the rudder's now trying to return it as well. So this accelerates the fin back hard the other way, and it overshoots. So you end up with the fin bending way across to the left, the rudder's to the hard right. It's twisting back around, which decreases the angle of attack. It's trying to get the airflow to drive the fin back to neutral. And the rudder still keeps on swinging around till it gets hard over to the other side. And then you've got exactly the same situation where you've got the aerodynamic forces from the angle of attack trying to drive the fin back to neutral. You've got the rudder hard over trying to drive the fin back to neutral, and you've got the elastic forces of the structure trying to drive it back to neutral. And you'd guessed it, it's going to rapidly overshoot back the other way. It won't take much of this before you start getting those horrible cracking noises out of the structure. You'll get large deflections of the flight control surface, pretty much going to the stops. You'll start building up very large deflections of the structure, and you'll end up with structural damage to the surface that the control surface is attached to. So your wing, your fin, and your tailplane. We can also get another form of flutter. For the sake of argument, we're going to call it wing flutter, but it can also be applied to fin or the tailplane. Not so common to experience it in sailplanes, but we'll talk a little bit further about what happened to the Phoenix. I actually think it was something along these lines that happened to the fin and the Phoenix. A lot of these structures on the aircraft can be referred to as what's called a cantilever beam, where it is exactly the same as if you have a ruler on the desk and you've clamped it to one end of the desk with your hand, and you've got a fixed end at the root end, and the free end is allowed to move around at the tip. So what we refer to as primary wing flutter is both wingtips bouncing up and down together in a symmetrical pattern, just like you'd twang a ruler on a desk. The fuselage would end up bouncing up and down slightly in reaction. Mr. Newton had these laws of motion. One of them says every action has an equal and opposite reaction. So as the mass of the wing is bouncing up, it's trying to drive the mass of the fuselage and tail down. So you end up feeling in the cockpit a lot of vibration, like you're driving over a corrugated road. And that's going to be in the order of frequency that you do your wing shape test at during the annual inspection. That kind of frequency is driven largely by the bending forces on the wing. So the bending stiffness of the wing, the centre of gravity on the wing. It's all about bending in that mode. You can get a more complicated version where the controls interact with this. Now, I've used the same diagram as before, and it's pretty similar, but the real difference here is it's the surface, the wing, fin or tail, which is driving the motion, and the control surface is just along for the ride. So what I mean by that, again, working from top left to right, bottom left to right. On the second image, you have let's say it's a wing, it is bouncing down and it leaves the aileron behind. The aileron has inertia, it wants to sit where it was in space. So it flaps up. It then, of course, helps drive the wing down a bit further, causing a fair bit of torsion on the wings, particularly at high speed. You get a lot of torsion from the ailerons. And the cycle repeats. You then get the wing bending down, has a nose up twist to it, so that's getting an increased angular attack, which is driving the aerodynamic forces to help drive the wing back up, along with the elastic stresses on the wing. As it starts bouncing up, the aileron is again got inertia, it's still travelling downwards, it flaps down a bit. And of course you've got that situation where you've now got, on the top right hand side image there, an increased angle of attack. You've got the elastic forces of the wing trying to pull the wing back up into shape, and you've got the aileron deflected down, increasing the aerodynamic forces, forcing the wing back up, and of course it overshoots. The main difference here is you're probably not going to get as much control deflection as you would as if it was being driven by the control surface itself. You're less likely to feel this through the controls, you're more likely to feel this through the airframe. It's the vibration through the airframe more than the controls. Splitting hairs a little bit, but it is a distinct mode. What you end up with, particularly with the ailerons, is this anti-symmetrical mode. One wingtip is up and the other is down, and you've got that bit of a S-shape or sine curve to the wings. And the fuselage will roll back and forwards in reaction to this. Something similar is going to happen if you get this kind of flutter mode happening with your vertical fin. As the fin's rocking around, it's going to have the rudder trying to remain stationary in space and start flapping around a little bit behind. It's the motion of the mass of the T-tail and the motion of the fin which is really driving the flutter event, and the rudders along for the ride. I think this is what actually happened with the Phoenix. Generally, with this anti-symmetrical mode in gliders, this is the first mode you tend to encounter in gliders. We've got these long, slender wings with thinner and thinner airfoils. We don't have a lot of torsional stiffness in these high aspect ratio wings with thin airfoils, and this mode is dominated by twisting more than bending. And you get that funny shape where the wing trying to bend up but then bend back down again, is because you've got this control reversal effect. As the aileron is going down, it's putting so much twisting force on the wing, it's lowering the angle of attack to the point where you're getting this negative lift rather than positive lift. There's a number of videos that I've listed there. I will show them. I'll show the SB9, a segment of the SB9 Flutter video first. The SB9 was a, excuse me, I'm just messing things up here. Came out of the Ackerflieg in the 1960s. It was a very early fiberglass glider. It was designed around the strength of the wing rather than the stiffness of the wing. So when they first flew the SB8, which was the first model, they encountered some pretty severe flutter effects very quickly. The wing was quite floppy. They built a new version, kept the fuselage, put longer wings on it, which was the SB9, and I believe this is the first version of the SB9 with these very long wings and very low stiffness. You can see what happens here. This is a brief animation of the expected motion of the aircraft. And you can see the response of the fuselage rocking around as the wings go through this crazy S shape. Because this aircraft has very flexible wings, whilst this is a great teaching aid, you can see that the flutter is expected at 90 kilometres an hour, very low airspeed. And because it's got low stiffness, you've got quite large amplitude. So it's very good for showing what's going on. Probably not so good for a real world example. I'll just keep this playing for a little while longer. There's another segment to this where they do it in slow motion. If someone can read German, they can let me know what that means. I think it's about 3.5 times slow motion. And you can see the input of the ailerons. You can see the flexing of the wings quite clearly in this slow motion footage. I'll go to the next video. This is a DG. This is a more realistic example of what you can expect in real life. I don't want to experience that ever myself, quite personally. Lastly, I'll show a video. It's actually a compilation video from a variety of sources. Start part way through it. This is a C-141 star lifter. It is undergoing flight testing. With the T-tail, the star lifter had some fin flutter problem. So this is where the fin is shaking around and the rudder is along for the ride. But it's an interesting example because you can see the response from the wings. The fin is rocking around, it's trying to roll the fuselage back and forth in response, and you can see it's exciting the outer wings. The view from the tail. And pause that there. I need to go to a new timestamp further on. There's quite a bit of odds and ends shown on this particular video. And about here. There's a variety of wind tunnel tests. One of the problems you get with military aircraft is they like hanging stores and heavy things on the wings, and this moves the mass further outboard and sets up all sorts of interesting flutters. Now that is very similar to the C-141, and you can see the twisting and bending of the vertical fin there. There's an example of horizontal tail flutter. That's primary fin mode with the bending and twisting. That's an interesting one of a winglet. So I haven't mentioned winglets so far, but you can get flutter in winglets as well. And I'll skip the ads. So you can follow those links. I'll publish this online and watch those videos or more at your heart's content. Quite a few different videos come up when you search for aircraft flutter on YouTube. And in the shenanigans here, I've managed to lose the some of the little windows I had pre-set up for participants in chat. I'll lose chat as well now. There we go. So Flutter causes. Primarily airspeed. Flutter is a high-speed event predominantly. By design, you want to have your flutter speed somewhere in the order of 1.2 to 1.3 times VNE. Flutter is, generally speaking, a function of true airspeed. So when you have increasing altitude, your indicated airspeed corresponds to a higher and higher true airspeed. At some point, you're going to cross over the flutter line. So aircraft fitted with an oxygen system will have to have a table next to their ASI showing a decrease in VNE above a certain altitude. Most commonly, it's 10,000 feet. Some aircraft I know have it starting at 8,000 feet. So in this particular example on the right-hand side of the screen, it's a mythical airplane, the Num Bum 6. Yes, that one with a really uncomfortable seat pan. A nominal VNE of 145 knots, a nominal flutter speed as shown there. If you were to continue flying at VNE as you increase your altitude, you'll eventually get to a point in the order of 17,000 feet where you'd be at risk of encountering flutter. Above 10,000 feet, you're supposed to have a decreasing VNE. So those people who have the good fortune of flying in wave conditions and want to go racing along the cloud line at VNE, yeah, be careful with that one. The other problem you can get is with leaky pitot systems, or block static ports. So your ASI is actually showing a lower airspeed than what the aircraft is actually flying at. Certainly caused quite a few problems over the years with airliners that have left tape over the static ports. Common around some of the tropical airfields is you get wasps and insects building nests inside static ports. Often causes your ASI to underread. One that I know personally was with a Club Labelle, had the pitot is mounted in the nose release. I had a flight where that pitot got disturbed and was pushed back into the release and had fallen down behind part of the release and was misreading. I got off aerotow and it felt like I was doing 60 knots. I was indicating 40. So I was fortunate enough to be creative with my feet and knock the pitot system to a point where it was reading correctly briefly and confirmed that 40 knots did in fact actually equal 60, and I then continued to do the whole flight flying at an indicated 40 knots and a real airspeed of 60 knots. As I mentioned before, if you're flying outside the envelope or flying in excess of VNE, all it takes is a bump in the air or a nudge on the controls for it to start. That disturbance, you need to get that motion going for it to accelerate and amplify. Other causes of flutter: change in the mass distribution along the control surface, change in the mass distribution along your wing, fin, horizontal tail. Anything that moves the center of gravity of that structure further away from the hinge point or the flex point will lower that resonant frequency. Most common one of that is increased mass at the wingtips, winglets, cameras mounted at wingtips. Heavy repairs, someone's gone and crunched up the winglet and crunched up the wing tip during a ground loop or something like that, and you've got a big mass of resin out there. Heavy repairs to the tailplane for a T-tail glider moves the mass of the vertical fin further up. One that bothers me for some of the aircraft with pencil tail booms, putting a lot of lead weight down the back of the tail boom to get your CGR for competitions. Yeah, in theory, that's going to lower the resonant frequency of the tail boom. So quite possible to start getting flutter of the tail boom bouncing backwards and forwards under certain circumstances. Really common one is people doing repairs to trailing edge damage and then having a lot of resin and extra glass back there, which moves the centre of gravity of further back from the hinge point. Absolutely critical to go and do the weight and balance on your control surface after you've done a repair. That's why it's now considered a major repair. You've got a high risk of changing the mass balance of the control surface. Another one is many aircraft have mass balance weights, often along the leading edge of the rudder. The ones I know of, there's been a couple of cases where the bonding of those has come adrift and they've fallen off. Large military aircraft, that's in my history, we had large lead weights along the elevator to get the elevator balance. Some of these developed fatigue cracks in the bolt holes, so these big lead weights were literally falling off or at risk of falling off in flight. And Chris has made mention that modern gliders now ballast the wingtip first and then inboard, and some can fly with only wingtip ballast. If they're certified to do that, Chris, then that's quite okay. The designers take it into account. One of the reasons why people go and put water ballast in at the root is so that it doesn't change the risk of flutter as much. If it's certified to do that, you're fine. If you're doing that outside of the flight manual, then I'd be really, really careful about loading up the outer tanks first, particularly if it's moving the centre of gravity further away from the wing root. Other flutter causes: excess control system free play, worn hinges, worn bushes and control rods, faulty bearings. I've already mentioned the story of where the bell crank mounts with free play or worn bolt holes in those causing problems. For those people with old school gliders with a elevator trim tab, yep, if they become disconnected, you've now got a flappy bit driving another flappy bit. That can lead to severe problems. I know of a C-130 Hercules where they had a aileron trim problem. They're operating well away from base. The air crew decided that they would simply disconnect the aileron trim and that it would remain happily out in the airflow, streamlined with the aileron. Note you had a flappy bit that was now had no resistance to its motion, driving another flappy bit, and they ended up with aileron flutter. Faulty control system dampers. You don't get too many of these in gliders. There are a couple of them kicking around. These are either friction plates or a fluid-filled container which acts as a motion damper. It's designed to take energy out of the motion of the controls, not necessarily give you any control resistance, but increase the resistance to fast movement and absorb some of that energy coming out of the system and damp the system. They can have problems, particularly if some of that fluid on the fluid dampers leaks out. Some weird ones can happen with gap sealing tape that's missing or only on one side in particular. I have heard of an interesting one where on a Twin Aster, I believe it was, with the rudder, during the Form 2, they replaced the seals on the rudder. They ran out of the plain sealing tape, but they had some combi tape. So they put the combination sealing and turbulator tape on one side and the plain tape on the other. And they ended up having, fortunately very gentle, but a bit of a rudder hunting. It was just moving left to right very gently. That was actually quite a reasonably low airspeed. But it was just bouncing backwards and forwards because of the difference in airflow around the fin caused by one side being turbulated and the other side not. Most likely you had the transition point moving forwards and backwards over the hinge line, causing a change in the pressure distribution over that rudder. One big one, structural damage, which, as a result of, say, a ground loop or a mishandled landing, which goes undetected, changes the structural stiffness in the area. And certainly my personal opinion with this Flutter event on the Phoenix is it suffered a mishandled crosswind landing at some point in its history. It's the tail wheels put a lot of side load onto the fuselage. It's done a bit of damage. It hasn't been seen or found. It's reduced the structural stiffness in that area and lowered the flutter speed to the point that in the order of 110, 115 knots, the aircraft encountered this primary fin flutter mode, so the top of the fin bouncing left, right, and the rudder was along for the ride. The rudder would have been contributing a little bit, but it wasn't the driving force. My personal opinion only at the moment, we haven't got any evidence of that. We might find a bit more when the fuselage gets chopped into, we can see exactly what's going on inside. So what do you do if you experience flutter? Slow down. Flutter is a high-speed event typically. Slow down carefully. Don't load the aircraft up with sudden Gs. If you've already got a lot of stress being applied to your aeroplane, you don't want to be adding a lot more stress. Don't go and pull 3 or 4 G and you'll pull up. Step 1, check controllability. If you still have control of the aircraft, consider landing. If you don't have control of your aircraft, consider stepping out with the parachute. Land the aircraft. Enter an unserviceability into the maintenance release. A major unserviceability is what I should have written. Get the aircraft inspected and find the cause and for any possible damage. By design, and it's in CS22, the aircraft is supposed to be free from vibration in all phases of flight with the exception of pre-stall buffet. So if you've got funny buzzy noises or funny vibrations coming through the airplane at high speed, you want to work out what's going on there. It's a damn good sign of something's not right. Now, you might have a little bit of loose tape, a little bit of loose control seal that's making the buzz. But if you're feeling strong vibrations through the controls or through the structure, then that's a real problem that needs to be resolved very quickly. And we should land immediately and resolve it. Don't say, oh, it's nothing and keep going. Certainly in the bad old days, rather famous story where at a competition where you had the start windows, you had a maximum height and a minimum height you had to pass through to start as the start line, and people were climbing up well above the maximum height at start and trying to dive through that V&E to get under that maximum height start line and start with as much energy as possible. And one aircraft came buzzing through the start gate and then continued on with the cross-country flight and landed and found that the elevator had split in half along the trailing edge seam as a result of elevator flutter from that dive way in excess of V&E through the start gate. So do we have any questions? You can stick your hand up if you want to have a chat, and I'll unmute you, or you can put some questions in the Q&A column or in the chat column. Oh yeah, there's a Q&A. Do you know how the Tailplane avoids flutter? The Tailplane, I think that is it? No, I don't. I did have a brief flip around through the internet while putting this talk together. I did see a couple of FE models for the Tailplane, and I did not look further into how they did it. That would have quite a high true airspeed. So Probably very careful design would be the answer. Was that a janter? I presume that's to the competition story. I can't recall what it was, to be honest. Some of the old timers might recall which competition it was and who was involved. Anybody else for questions? Alan Wilson, Puhartz and others, elevator trim tape one rather than fly loose. Yep. All right, well, thank you, everybody. I'll call it quits here. I will stop the recording. I hope everyone's gotten something out of the presentation tonight, and once the recording's finished, I will get it put up on the YouTube channel for Gliding Australia. Thank you all.
Thanks, Anthony. Well done.
Not a problem.